In case you weren't here in the morning, I'm Nigro, and this is Taylor Akers. We organized this session on, what did we call it? Seed sourcing for resilient reforestation. Basically, there's a lot of interest in sort of what should we be planting now that our climate is changing, and there's a lot of different, opportunities and different strategies you can take with that. So that's kind of what this session is about. It's just looking at how a variety of people are thinking about this topic. Our first speaker is Taylor Akers. Come on up.
Okay, that works. Great. Oh, hello everyone. My name is Taylor Akers, and I'm really glad to be here today. Thank you all for coming. I'm working with Nigro and Mike Battaglia with the Forest Service at the Rocky Mountain Research Station. I'm an ORISE fellow, and we're working on this project called Seeds for the Future, and it's all about prioritizing cone collection for future-focused reforestation. So while many of us here at the Fire Ecology Conference can really appreciate wildfire as a fundamental ecological process, at the same time, we have to hold the truth in our hearts that fire can be a very destructive force. And we know that the wildfires that are burning today are burning much larger patches at high severity than historically. And that causes a lot of ecological and cultural damage. And regeneration, I'm just gonna stay here real quick. Regeneration within these post-high severity landscapes is really limited by the distance to the nearest available seed source, and also the extreme environmental conditions that any potential seedling would face growing in such an extreme exposed environment. This figure is really nice. I like it because it shows the possible trajectories of a regenerating forest that was previously forested, had a high severity wildfire event, and in some cases forests are regenerating immediately, as in the top panel. In other cases, forests are delayed in their regeneration, they're experiencing a change in the dominant tree species, or they're failing to regenerate into forest-type vegetation communities altogether. And so these latter three scenarios often impede some of our management and forestry objectives, and in order to prevent this forest-type vegetation conversion after high-severity wildfire, we need to actively reforest our previously forested lands by planting seedlings. And here is an example where we have the Cameron Peak fire boundary in red, and this fire burned primarily within the Arapahoe and Roosevelt National Forest, which is the black boundary in this map. This is northern central Colorado, for those of you who are not familiar, and it's just outside the city of Fort Collins, where my colleagues and I are traveling here from. This is zooming in a little bit further on the Cameron Peak fire, and I just want you to notice that all of the area in red is where the fire burned at high severity, and it's approximately 80,000 acres. So really large patches of high severity burn where regeneration is limited and we need to replant. This is another map of the Cameron Peak fire, but here I'm showing all of the planting needs that the Forest Service has designated as needing to be replanted after the fire. It's approximately 50,000 acres. It's a really large area that needs to be replanted, and we need a lot of seed for that replanting effort. We have the reforestation pipeline as a framework to follow for how we can go about reseeding areas after high severity wildfire. And it begins with collecting seed in the wild, or seed orchards if you have them. In the Southern Rockies where we're from, we don't really have seed orchards. And then those seeds are grown in nursery and outplanted. However, we really have insufficient infrastructure to accomplish these goals. We have a lack of diversity in our seed bank. We have a lack of sufficient space in our nurseries. And as many of us are aware, we have a lack of workforce in order to really carry out all of the steps in this process. Additionally, another complication we're facing is that the traditional seed sourcing pipeline assumes that local is best for collecting seeds. In the national forests, normally forest managers collect seed as close as they can to the planned planting area. However, we know that our temperatures globally are increasing, and other climatic factors are not following historical trends, and the geographical niche for species is shifting, with a general trend for species to move to higher elevations and poleward over time. An added complication for that, if you work in forestry, is that trees, at least in the dry forests of the western United States, tend to grow very slowly, and so this shift, the species are not able to shift in their range on their own without some help from forestry. So silviculturalists are adjusting to these complications by implementing forestry-assisted migration. Now, if you were in our earlier talk, we had a great discussion about assisted migration, but for those of you who were not here, I'll just go over kind of what assisted migration is all about. So in this panel, we're showing just assisted population migration, which is one form of assisted migration. There are 3 different tree species, and you can think of them as occupying a historical climate gradient. And here we're using temperature as an example, where across the landscape the temperature goes from warmer to cooler areas, and different species of trees would occupy different niches in that gradient. And within a species, there are different populations of trees that are locally adapted to their particular area. And those population differentiations are based on many factors, but we're primarily looking at temperature in our study because it is the most consistent variable in the literature for the Southern Rockies coniferous forest species that we're studying. And with assisted population migration, we're just taking seedlings from one population and moving them to areas where other populations of the same species already exist. With assisted range expansion, we are taking seedlings from current populations and moving them just outside of the range of the where the species currently exists, but not further across any kind of geographical barrier like the Great Plains or across an ocean. So we're staying within the range of what would be the natural species shift for that species. Okay, so if we know that we have to actively replant after high severity wildfire in order to maintain our forests, the questions that remain are, which populations will be the best adapted to the future climate conditions of a given planting site? We also want to know, how do we prioritize actually collecting cones or seeds in those populations that we're interested in? So the goal of Seeds for the Future is to create spatial data resources to help guide managers through making these decisions. Our case study is within the Cameron Peak fire boundary that I've already shown you, just outside of Fort Collins. And in this map, we have the same planting needs areas, but broken into operational sizes, and we're calling them potential planting units. And because populations of trees are locally adapted, we have to further narrow our range for our case study and look at groupings of trees that we're going to be planting, and we group by elevation band. So in yellow are 20 units that are within the 9,000 to 9,500 foot elevation band, and those are the specific areas we're looking for in our case study. So in order to prioritize cone collection areas for our case study, we are looking at a variety of what we're calling priority factors. We're considering tree maturity because we have to find areas where there are actually going to be cones on trees. Feasibility because we have to consider access for our field crews. And we're also considering the risk of local extinction because we want to conserve those locally adapted traits. So we add all these factors together and create what we're calling potential collection units, or PCUs. And our first factor of tree maturity, we're using tree height as a proxy, and we essentially filter out any areas on the map. Again, we have the ARP here, and in orange we have only areas where trees are greater than 10 feet tall. And we do the same spatial exclusion for areas where trees are only greater than 5 inches in diameter. For feasibility, we look at areas and exclude any area that's greater than a half mile away from a road, and only consider areas that are less than a half mile from a road, and then we assign an inverse score to those areas and prioritize areas that are closest to roads. That would be the darker pink color in this map. We do the same spatial exclusion for slope, excluding areas over 24 degrees, and in the map you can see the darker purple are the flattest and highest priority areas. For risk, we are looking at the probability if a fire were to occur. It's the probability that it would become a crown fire. And we're using this as a proxy for high severity wildfire risk. And in this map in orange, the darker colors represent areas that are highest risk for local extinction due to crown fire, and we prioritize those areas higher. We then combine all of these factors together, big sandwich of data, and in the green in these maps are all of our potential collection units. We've also filtered out any really small discontinuous patches, and all of the areas in green meet our basic priorities. They would be decent places to go scout and look to see if we have confined cones there. And there are 6,400 PCUs in the ARP, but it's still a huge amount of area. We cannot send field crews out to all of those areas, so we have to further filter. And the way we are doing this is by independently evaluating the climate match of our case study. So this is how we're doing it. We're looking at the future climate of our planting unit. Those are the 20 yellow polygons that I identified earlier as being within the Cameron Peak fire boundary that we want to plant. So we look for areas where the future climate of these planting needs is equal, with some degree of variation, to the reference climate of our collection unit. And the collection unit could be any of those green areas we identified in part 1. We're looking at the 1961 to 1990 period as our reference climate because trees are most affected by climate and need to express the ability to adapt to their environment when they're very young. And the trees that we're collecting from, the mother trees, would have been between 35 and 65 years old during the reference climate period. So they are more adapted to this earlier period. The trees that we will plant today in the future, during the future climate of 2041 to 2070, would be between 15 and 45 years old. And this mid-century period is really good for planting because it's close enough to be relevant to young seedlings and still far enough to be relevant for trees that are beginning to reach reproductive maturity. We're looking at using the climate scenario SSP2, it's the middle of the road. And we're also looking at the mean coldest month temperature as our primary climate variable because it is the most consistent in the literature for what distinguishes populations of coniferous trees in the Rockies. Great, so here's another map of the ARP, and again we have those same 20 planting units that we have for our case study, and in blue are all of the areas in the ARP, and we're bounding that climate match to the ARP, where the future climate of the planting unit is equal to the reference climate in the ARP. So the scale of blue is showing the number of planting units out of the 20 that share a climate match. And it's important that we collect in these areas that share climate match because resources are very limited. And that's why we have to find areas of overlap where our collection units in green overlap with the climate match in blue of our planting units. This is the same map, but with any collection units not overlapping with the climate match area filtered out. They're not going to be further considered for these planting units. And then we further filter those collection units out to only consider areas that meet at least half of our planting needs for this case study. And this is the same map, just zoomed in a little bit further so that you can see those 350 potential collection units that are within the climate match area. And then in the next step of our process, land managers will be able to further filter down those planting units by other objectives that they might have for their forest. For example, managers might be targeting a specific species and therefore they would filter out those collection units based on where that species is the most abundant. They can also filter by inventory metrics, geographical constraints, and also what is in the current nursery inventory. And our main result is that out of 6,400 PCUs in the ARP, 1,700 meet at least one of our planting needs, and 350 of them meet half of our planting needs. So to get the biggest bang for our buck, these 350 PCUs are our highest priority, and sourcing seed from any one of these units would source future focus seed for approximately 4,000 acres of planting needs. And while land managers have some tools and resources available to help them decide where to plant after wildfire, other tools kind of help guide choosing populations of trees that will best match their planting needs. There's still no tool or resource available for managers to actually know where to go on the ground to collect that seed. And that's where Seeds of the Future comes in to fill that gap by narrowing down thousands of acres into a small set of high value collection units that are specifically going to address the needs of their planting sites. Moving forward, we hope to integrate Seeds for the Future methodology into some other existing tools that already identify high priority planting needs so that managers will automatically see a map produced of high quality collection areas that will meet their needs. And if you're like, what tool is she talking about? We are having a fire circle after this talk and in the Southdown room where we're going to talk about all the different seed sourcing tools that are available, and we'd love to have you there. So with that, thank you for your time and attention. If you're interested in following our project or seeing the source code, you can check it out on GitHub or contact us. Thanks.
You have 3 minutes for questions.
Yes?
Hey, that was super cool.
Thanks.
Thanks for sharing. You mentioned that you'd like in the future to give managers the option to filter by like some productivity metrics.
Yeah.
Could you talk a little more about what that means?
Sure, yeah. So for example, if managers are looking to avoid areas that are really dense, they could filter by canopy cover to avoid, going into dense areas and look for areas that are more open. And the same can be done for any forestry metric, because we're planning to plug in like the FIA database into the tool so that basal area or QMD, any metric that's available on spatial scale can be used to narrow that down. And the same can be done for species distribution information too. Yeah,
Sweet,
thanks for the question.
Curious, what was the average or median elevation of the reference condition that you found that you would source the seed for that 9,500?
Oh, that's a great question. Yeah, so for the 9,500 foot elevation band, what would be the collection unit elevation?
Yeah, so I was trying to reflect the statistics of
We haven't looked at the statistics of it, but it's always lower elevation.
Yeah, I can tell it was definitely lower. I'm just curious how much lower.
That'd be a really fun
It looked about
additional
7,000
question.
feet just based on my knowledge
It
of
looked at like
elevation.
7,000
Yeah.
feet. Yeah.
Yeah.
But we could add that as
Yeah, I
another
think that's a good idea.
analysis to add onto our
actually.
paper. Great idea. Yeah. Thank you.
I have a quick question. How good is the data as far as, or how easy is it for you to make assumptions about the presence of the target species?
That's a
in
great
those
question. That's way beyond my pay grade. But we're using tree map data mostly, and we've also considered using big map data. There are some others like Stewart's Little's distribution. So that's, we only have what's most of it, what we can access, but it is questionable. But I think the take home there is that these units are designed for planning field trips, and then you really have to go out in the field and get some ground truthing information before you can really send a crew out to collect cones.
And then to make the delineations of the units, was that just sort of, did you merge naturally with the distribution of the ecosystems you had, or how did you just parse them? Sorry.
There's it's just a spatial data tool we used in the software program we're using that does it, and it just does it by size.
Okay.
You give it the number of breaks you want,
I
and then
see.
it breaks it up in equal sizes.
Cool.
Okay.
So we did it independent